Welcome to all of you that clearly are passionate about trying to understand the universe around us. One of the fantastic thing about this talk is that to me randomly, I got a phone call from this office that we'd be interested in giving a talk on the God particle. And it was so fantastic to know that this kind of interest was coming from the general population and this type of stuff. So we jumped at the opportunity and hope we could unravel a little bit of all this hype that I'm sure you've heard about. All right? So let's get right. Exactly 1 month from now, right? 1 month away, on the 4th of July, today's 4th of August, from the time you see that date, 4th of July, you punch it into the internet, you're going to see 4th of July means fireworks, okay? But the real fireworks this 4th of July was happening in the European Center for Nuclear Research, right, where the real fireworks was happening. I mean, look at the picture of those scientists. Have you ever seen a group of more tense people? I mean, it's worse than the parents of the Olympic people that are performing, right? And what was it they were waiting to see? What is causing that tension, and what is that real fireworks that was happening? It was a long-awaited search for something. Has it been found, and are they on the brink of it? And that's what today's talk is about. You've heard about it, the God particle. What is it? Did they find it? The Lord of the Rings. Behind us we've got LHC, that's a Large Hadron Collider. It's run under CERN, and it crosses the boundaries of actually two countries, Switzerland and France. And 100 meters below the surface of the ground, you've got this 27 kilometer ring. And what is its job? Its job, another name for the collider is self-explanatory. Another name is an atom smasher. Its job is to speed things up and smash them. All right, if as children you took little toy cars and the great joy you experienced in smashing them, well, it's just big toys for big boys and girls, and very, very expensive toys. Okay, so the Large Hadron Collider, its main mission, it was operational in 2010 at a cost of $10 billion. Okay, and its job is to answer this question that we're going to look at today. And you tell me by the end of the talk if you think it's worth the $10 billion. So 4th of July and thereafter, this has been in the news. All right, we found it. We found the Higgs boson. But right alongside it, you would always see the God particle. A very familiar face. Everybody recognizes him. Stephen Hawking. He lost a $100 bet over this. He bet that we were not going to find this, well, at least see the hints of this particle at this time. But you see, in a case like this, that's one of the best $100 that you could lose. You wouldn't mind losing $1,000 to be proven wrong in such a case. 2012, 4th of July, something changed dramatically. All right, and many people don't understand what is it that happened, because life seems to go on as normal. But the story didn't start today. It started 3,000 years ago in ancient India and Greece. All right, so there they are. And what was this story? It was the idea and the concepts that began to develop that what is matter? All right, all around us, you are matter, right? And you can, if you are cooking in the kitchen and you're chopping your salads, well, see how small you can chop it, and you can chop, chop, chop. How small can you reach a point where you could no longer chop this thing? And that's what the concept and the idea behind the atom. The ideas began 3,000 years ago, all right? And it's a bit of it's not quite clear cut. Is it in India that the idea was born, or was it in Greece? The records actually show they're older from India, but the ideas or as often happens in science, did they arise simultaneously? It's a very common thing that often happens in science, that totally independently different regions come upon similar ideas. So that's up for debate. But the thing is, people started thinking, what is the smallest particle that I can get? Well, we fast forward to 19th century. 1800s. All right, that's a phenomenal amount of time for the basic concept of what's the smallest particle that I can get to see where it's leading us. All right, so this journey is 3,000 years ago, 3,000 years old, but the last couple hundred years is just a phenomenal leap. And in our times, as you will see, the last maybe 50 years, 40 to 50 years has really been fantastic. Anyone recognize? I mean, he does look a little villainish, doesn't he? Why would he be the villain? That's actually Leon Lederman. And I call him the villain. He's the crook that made the term God particle famous. He's actually a Nobel laureate physicist, and he wrote this book in 1993. If the universe is the answer, what is the question? The God particle. And it really captured the imagination of the general population. And why I call him the villain is because on behalf of all fellow scientists, let me say it here and now and then, that this term God particle is actually hated by scientists. To refer to this particle as that, it has a name, they will tell you. It's called the Higgs boson. Okay, but you know something? I mean, as someone who's involved in a lot of science popularization, I think what he did by calling it God particle has popularized it way more than if it was the Higgs boson. But all is not lost. There's a reason why would he have called it the God particle. Well, one was that it was such a miserable particle, so elusive, so difficult to find, that he actually wanted to title his book The Goddamn Particle. The publishers rejected that, so he resorted to calling it the God particle. Okay? So, but that aside, and that is his second reason why it's called that. The reason really is that this particle is so central to physics today, so crucial to our understanding of the structure of matter, and has been so elusive. All right, and the fantastic thing about the human spirit is that they don't give up. And the more elusive it is, the more they go after it. They'd find the money, they would. I mean, there's something in science called blue sky research, that you put money into areas that have no tangible and anything that will affect anybody's life, whether it's food or technology or anything. Why do it? It's absolutely one of the most essential areas that must remain, and that's the power of thought, that's the power of freedom. And many times, and those could be many other lectures I could talk to you about, where such unforeseen results led to tremendous development. Okay, so call it blue sky research. So who's our hero of the hour? Let me get my water. That's Peter Higgs. That's him looking on as the results were announced. And as you can see by his face, his remark was rather dazed but very pleased. So you know where he comes from. Right? He's a Brit. He's from Britain. So the Higgs particle, the name is owed to this gentleman. And when did this idea hit him? I was having a very interesting talk with the Honorable Winston Ducaran before coming here. And one of the things I told him, I was really amazed that a request for such a topic came from the office. I'm just being open. And he said, you know what? A couple of us were walking. We usually do this. And some of our best ideas come when we are walking. And they were talking about what are the latest discoveries that are happening. And one thing led to another, and it led to Higgs boson. And I looked at him and I said, guess what? In our talk, you will see today that the eureka moment for Higgs, Professor Higgs, came when he was on a walking trip to Cairngorms, and the idea hit him about this particle. So folks, get out there and walk. All right, there's something about walking that clears the mind, that gets the neurons firing. So his eureka moment came while he was walking, and that was in 1964, right? We are 2012 today, 48 years later. Note, his paper was actually rejected when he submitted it. And furthermore, when it was published, he was strongly told by senior staff and so on that, what's wrong with you? You are committing professional suicide. All right, get away from this kind of hypothetical area. It's not going to lead you anywhere. And one of the things Professor Higgs did say was that he didn't believe he would have lived to see the day. Okay, so as we get into the talk, and we will open it all up, what all the story is about. So Guys, it's never too late. Have faith. We can always, comes a time when we could say, I told you so. All right, so it took Professor Higgs 48 years to, well, he didn't actually make the remark. He's a very gentleman kind of person, but really that's what it is about. Then it's the Higgs boson. So we talked about what's Higgs, Professor Higgs. What's the boson part of it? And very few people are actually talking about the boson part of boson. And that term comes from Satyendra Nath Bose, and I call him the unsung hero. He is a person in the 1920s who actually formulated the existence of these kind of particles. He was in India, sent his paper to a journal. It was rejected. The history of science is of great motivation. You are usually rejected with great ideas. It's persistence, and a lucky break, right? So his paper was rejected on what he had accidentally found. The story of science is really, really interesting. How did he come upon this particle? He was giving a lecture and he made a mistake. Right? While he was writing on the board, and the mistake was as simple as if we take a coin and we flip it, and I can ask you all, what are the chances that I will get ahead? Come on, shout it out to me, somebody, mathematician. What's the chance of getting ahead? 50%, okay? Right, so while he's teaching a lecture on these particles, he wrote 1/3 accidentally and got the right answer. And that's what cued him. Wait a minute, does that mean that particles at the very, very, very smallest scales are probably behaving differently from how we understand? So Bose's contribution to these particles came that way. Paper was rejected, so he wrote to Albert Einstein. Albert Einstein looked at his work and saw that there was merit in it, and on his behalf sent the paper to a very reputable journal and Albert Einstein is going to attract attention. Satyendra Nath Bose has never received a Nobel Prize. Okay, so that's why I am going to give you the story of the development of these things. But a host of other scientists have, on these same particles and understanding their behaviors, received Nobel Prizes in physics. And this is a famous trio, Glasgow, Salom, and Weinberg. I'd like to point out some of our own historical people. That's Abdus Salam, professor in physics, and for the Nobel Prize ceremony, he ensured that he wore his traditional gear to it. It's always a big coat and tie event, but he went dressed because he's born in India before its partition, but later on from Pakistan. He has been written off pretty much by Pakistan, although they're only Nobel laureate, and that's another story, okay? So he passed away in the 1990s, but all these gentlemen made contributions to this particle. We're getting to it. What does this particle have to do with anything at all? The Higgs boson, or the God particle, I'm fine with either name, has to do with the structure of matter on the smallest scales. That's why I told you the story began 3,000 years ago, not today. All right? And now I've had some really interesting conversations with the people just before the talk. There was Vito who was also telling me that when you realize the scale of things in the universe, it's mind-boggling. It will absolutely make you totally insignificant. At the same time, that makes you very, very special as well, because you are here in this insanely massive universe, which against all probabilities, you should not be here. Okay? So that's matter on the largest scales, but to be able to understand it, you have to zoom in onto tinier and tinier and tinier scales. In that scale, you talk about quantum physics. So the Higgs boson has to do with matter at this scale. So a little physics for those of you that skipped class when you ran away from your physics class. So I have you back in here. This is your atom. On the scale of things, it's one of really the larger counterparts. The question is, what scientists want to know is what are the basic building blocks of life? What's the minimum number of particles that I can have to build you, this room, this classroom, the entire universe? Massive undertaking, won't you say? So they thought for a long time the atom was made up of protons and electrons and neutrons, right? High school physics, you've done some of that. Then Not too long ago, just a few decades ago, they discovered that protons and neutrons are made up of further subparticles, and that's the quark. Okay, so the aim is, what is the smallest basic unit that everything is built up from? Okay, so we talked about the atom. Atom means uncuttable. All right, so what are we going down to? So the quarks, as far as we know up until today, they are the basic constituents of matter. No one has been able to cut the quark any further, and there are 6 of them. And it shows you the ingenious and probably the late hours that scientists sometimes keep with their inventive names for things, okay? Don't worry too much about that, just simply different types. So the basic stuff that all matter is made up of is in 2 groups, leptons and quarks. So all matter could be made up of these guys. You have other types, but these tend to be unstable and so on, but they're all also basic entity of matter totally. I'll come back to that in a bit. So this was the question. So one question is, what's the smallest fundamental entity that can build the entire universe? The second question actually is, why does it exist? All right? In life, in the universe, there's matter and there's energy. There's not much else, okay? And then there'll be the forces between them. So the question that these guys came up with is that, why does matter exist at all? And where does this mass come from? I'm going to come back to some of these and explain it a little bit better, but let's continue to build up our story. So Higgs said that the mass that quarks and leptons have comes from it passing through a kind of a field, and the field is putting a drag on it, and that slowing down manifests itself as mass, right? Folks, no excuse, we are not to blame the Higgs particle anymore for our weight issues, all right? So there's one more excuse we can add to our list, but not the Higgs boson. So the Higgs boson is these particles that are creating a field all over. And this is, if you're doing some reading on the internet, you keep running into this particular analogy that it's like a superstar or a celebrity, or in our case, Honorable Winston Dukeron walks into the room, you'll find that people will gravitate towards him. And the more people gravitate towards you, the harder it becomes for you all to move as an entity. And that harder that it becomes to move as an entity means it's equivalent to greater mass. So smaller the mass, it's going to zip around very easily. The larger the mass, there's a resistance to motion. And that's how the Higgs field, now it's not the Higgs boson, that's the real star. The real issue is something called the Higgs field, which by manifestation should produce the Higgs boson. That's what the search is for. And where does all of this fit in? It fits into something called the standard model of the universe. Isn't that a nice term? Right? Scientists also quickly run out of term. So the standard model is, what's the basic items I need to build the universe? Call it that. Okay? And there it is. So far, the entire universe, you, the chair, the room that we are in, the laptops, at its smallest scales, should be able to be somehow built up by simply 12 particles and this guy, the Higgs boson. Since the 19th century, when research and everything started on these things, and in the last few decades, all these guys were found. They were predicted, they were found, except for one elusive fellow, and that's the Higgs boson, and that's why it's such a big deal, right, on the 4th of July last month. So quarks make up your protons and neutrons. Leptons, keeping it very simple, are your electrons. Then the question becomes, how do these things interact? Well, they interact by force carriers. And there are, right, that's the same thing, just a prettier picture, I thought. So, there are simply 4 forces in nature. Isn't nature beautiful? Nature is simple, you know. At the end of the day, you don't need a 1,000-page manual to tell you what the universe is made up of. 12 particles, folks, and the Higgs boson. And those basic particles, how do they interact? Well, they interact by 4 basic forces. There are no other forces in nature except the 4 that you're seeing up there. There's the electromagnetic force, strong force, weak force, gravity. Electromagnetic force, everybody should have experienced that. If you've used a magnet, you've experienced electromagnetic force. Strong force, thank God for the strong force. Strong force is what's keeping the nucleus together. If the strong force did not exist, we would not, none of us would be sitting here. Weak force causes the disintegration of the nucleus and decay processes. And who doesn't know gravity? Thank God for gravity. All right, and that's it. That's it. There are 4 fundamental forces in nature. So the strong interaction, why is it needed? Why does it exist? You're going to have physics 101 here today. We can't get away from that. Okay, if you have 2 positive charges, and I know I am seeing the physics teachers in my audience, my former students, some of you, I recognize you. 2 positive forces, what's going to happen to them? It's going to fly apart. 2 negative forces, it's going to fly apart. Now, the nucleus is made up of protons and neutrons, all right? Neutrons, what kind of charge? 0, neutral, okay? So they don't matter. That's why they took a lot longer to be discovered, because they're sitting there innocently. Those that cause an interaction, and some of these things you can actually translate to politics. Physics easily translates. Those that cause an effect on things, they will be discovered. Now, you've put 2 protons in the tiniest little place, and it just takes very basic equations, and I promise no equations in this talk, to show that the power of repulsion between them is phenomenal, which means a nucleus should not exist. A nucleus is made up simply of protons, all these positive charges in a tiny, tiny, tiny area. And yet, you are sitting in front of me. The nucleus does exist. The nucleus exists thanks to the strong force. The strong nuclear force operates in such a way that it keeps positive charges together. And if I had my class by now, I would have been throwing a pen at some of the students to throw it back to me, because it's an exchange force. It throws the particle back and forth, back and forth. It must obey that rule, and in the process, it stays together. Okay, so the nucleus stays together because of the strong interaction. Electromagnetic forces, well, we talked about them. Now, we're not going to get very technical at all. I've stayed away from really the biggest words, okay, except for gravitational. The gravitational force, that's the one to watch. That's the trickster in the entire group. It's very, very weak, okay, but never ignore the power of the weak. The gravity, while it's the weakest force, is the one that eventually wins in the entire universe. Because if gravitational forces did not keep matter together, there'd be no stars, planets, human life, you sitting in that chair, right? You'd all be floating around. Might be fun, but gravity is what keeps us there. But it's a very, very, very weak force, so it does not play such a powerful role at the atomic scale. As mass increases, gravity becomes more dominant. So the story of the universe of physics is simply 4 forces. Gravity, keeping us seated and doing all the wonderful things we do. The strong force keeping you as an entity together. Electromagnetic force causing all these exciting reactions and things like that. And then the weak force operating within the nucleus, causing processes happening there. So the physicists wanted to know, it was not good enough. It's not good enough that we've divided all particles into 12 fundamental particles and the Higgs boson, 4 fundamental forces. They want one theory, right? The longing within the physics community is that there must be a grand unified theory that will bring together all the 4 forces. And you know, they've done pretty good. Physics has been able to combine 3 of the 4. Who you think is a troublemaker? Gravity, okay? And Albert Einstein spent to the end of his days trying to develop the grand unified theory, but gravitational force has been the troublemaker in all of it. So the story of gravity is tied in with the Higgs boson. We haven't ventured off our topic, right? In 1665, a wonderful thing happened. Well, it's so sad, it's not precisely that. Newton got hit on the head with an apple. Now, as I said, the story of physics is wonderful. Why did Newton get hit on the, saw an apple falling and it triggered those thoughts? Actually, he wasn't walking, but he was outdoors, all right? And that's because there was this plague in London, and they had to send they had to close down the institutions and send people back home. And he was sent back to his farm. And there, in the silence and the quiet, some of the most amazing thoughts emerge, right? So gravity, force, right? Newton, we owe that to him. And then a couple hundred years later, who could that be? Your most famous scientist of them all came and said that gravity is not action at a distance, doesn't make any sense. He says, you know what gravity is? Gravity is curvature of space. And when he did the physics for it, he made predictions, bang, he was on target. Albert Einstein is one of the fewer scientists that were a celebrity in their lifetime. And this is a very famous picture of him because he had the paparazzi behind him. Normally it's celebrities and movie stars. No, but we have a scientist who paparazzi followed everywhere. And one day in frustration, he turned around and stuck his tongue out at them. And of course, that picture is immortalized. But today, what we're focusing on is 2012, several hundred years later, that what role in mass, in the production of mass, does this particle called the Higgs boson play? So, general relativity, 1916, right? Curvature of space-time gives you what you know as gravity. And then, but what general relativity doesn't explain is where does mass come from? It tells you how mass behaves, and so that Newton was able to show that. And so that's what the search continued with. Here's this quotation from Einstein, which a lot of understanding how science happens is to understand the philosophy behind it and how it happens. 1,000 experiments will never prove me right, but one experiment can prove me wrong. And that is the reason why Albert Einstein actually only has one Nobel Prize, and which is in something called photoelectric effect. You may not even hear of, and not on relativity and general relativity, because his models are still being proven. If one experiment shows him to be wrong, in the words of Richard Feynman, one of the greatest geniuses actually after Albert Einstein. If you don't know him, do look him up, make a note of his name. He says, it doesn't matter how beautiful your theory is, it doesn't matter how smart you are. If it doesn't agree with the experiment, it's wrong. And it is these thought processes and the way of thinking that I think distinguish scientists from sometimes different modalities and so on. It's not about whether we like it. If the evidence says we are wrong, you are wrong. Okay, and that's where the shift in thinking occurs. So experimentation becomes a big part of it. And Higgs, Professor Higgs and group, several people predicted in 1964 that there should be this boson. So in 2010, the Large Hadron Collider was commissioned, it was opened up, and that's just 2 years ago with this major mission. And what did they do? They, as I said right up front, if I have a ball, if I have a beautiful marble, and I want to see what's inside of it, what do? Smash it. Okay? If you want to see inside an atom or see the effects of what's going on, you've got to smash it. All right? So that's why we want to smash atoms. And what they do is they collide protons, right? Basic protons in these huge experiments. Some of them are thousands of tons. And then wait to see the fireworks. So that's the ultimate fireworks. So this is one of the experiments that was used to show that there is a possibility of the Higgs boson. How many collisions? 800 trillion collisions. All right? So patience is something you learn from science as well. To look to see if they could actually see this thing. And more than one team, there are about 3 teams that have been working on this project. Now the thing is that this particle, as hypothesized, its lifetime is so short that if you blink, you miss it, right? As those guys will tell you. It lasts only a fraction of a second. So your best next bet is to see its effect on things or products of it. And that's what happened. So on 4th of July, the announcements was made that the CMS, as the Atlas team and the CMS, two teams, independent, and that is another hallmark of good science, confirmed that they had seen something of a particle that implied that there had been a Higgs boson. I mean, the rest of it is just the technical aspect of it, that what is the chance that they are wrong, and that's how science is done, okay? I mean, there are few things, frankly, especially at the quantum level, that you can say with any 100% certainty. But you could say pretty good that there's one chance in 3.5 million that it was a chance thing that happened. And with that level of accuracy, the scientific community can announce that a particle has been discovered. So Vivek Sharma heads one of the teams that actually found the discovery. And Wilczek here is a Nobel laureate physicist, and this is what they said. All we can tell right now is that it quacks like a duck and it walks like a duck. And he says, well, if it looks like a duck and quacks like a duck, it's probably at least a bird. And that's what the excitement is. Okay? Now, I have to bring in a part of it's not just about explaining the Higgs boson, right? It's about explaining how science is done. Do some of you remember not too long ago a story about that a particle faster than the speed of light, that neutrinos were traveling faster than the speed of light, and it hit the headlines, which is also sometimes a risk of science and media and that type of stuff. Have you still been following up that news? What happened to it? Okay, right, and that's precisely. So sometime last year there was this huge news that there was a particle traveling faster than the speed of light that had been discovered. And it sent the entire scientific community in mayhem, because if it is right, it's back to the basics. Well, this is one of my students sitting there. I don't know if you were not in the class at that time. My students got really excited. They were like, Miss, does this mean we are not having exams anymore? Is our course cancelled? And I said, not so fast. And that not so fast really worked, because within months, now the thing in science is one team gives a result, other people start to try and confirm it independently. And it turned out to be a fluke in the equipment. And so we could all go, phew, exams were held, and I must say the students did very well in relativity. Okay, so the case with the neutrino was an announcement of a result that threw the entire understanding of science into mayhem. So you watch it with great caution, okay, and it turned out to be wrong. The Higgs boson is a prediction that they've been hunting after. Do you see the difference? Faster than speed of light is not something that's predicted that one is looking for. It is the results of relativity. But the Higgs boson since the 1960s has been predicted, and research has been going on. And as we know, it was found, and it is intimately tied up with mass. What gives matter mass? Okay, and now some really technical stuff. I'll see if I could bring it down to see what the concept of mass is. All right, and so there is a scientist there, and that's actually, look at the size of it. This is the Large Hadron Collider, buried under the ground, right, 100 meters below the Earth, simply smashing head-on protons. Well, of course, it has given us some entertainment too. Okay, so those of you that need to collect little jokes and whatnot, you wouldn't have had that before. Okay, so this is the latest joke in our joke books. So how does all of this affect our understanding? The Higgs boson has to do with matter on the smallest scales, but its implication is about the universe on its largest scales. Because those that cannot afford $10 billion to test their theories can sit with paper and pen and hypothesize to what's happening with how the universe began. All right, so the beginning of the universe, the early universe, is often called the poor man's collider, because the conditions at the start, well, we always have to put a question mark here, and we don't know what happened at t is equal to 0, but I could tell you that at t to minus 10 to 43 seconds, we have a pretty good idea. Okay, and at that time, in almost infinite temperatures and extremely high densities, and in such a case, all you could have was the fundamental particles, only energy. At first, only energy, not even the particles come later. And that's where the question lies. Right? The question is, well, if we have a universe which is so hot, which is so dense, the pressure is so intense that you've only got all this energy happening in there, and it starts to cool off, because somebody already mentioned the Big Bang before me, right? It begins to cool off, and matter appears. Now, the thing about us scientists, all of us doing anything, is that we know matter exists. Why do we know that? Right? We are all here. So the questions become bigger. Where does it come from? How did it form? And that type of stuff. So at first, there's just all this energetic soup. There was not matter at first. And this is the words, I want to avoid things like symmetry breaking and quantum field theory, right? So we have not said those words. But suffice it to know that early in the universe, there was not matter at first. And the physics says that it's easier to not create the matter than to create the matter. It's easier to have a universe of just massless particles running around, happy as ever. But if that happened, you wouldn't be here. We are here because matter did form, it did have mass, and then, of course, gravity, the miserable force, did take over, like the hair and the tortoise. It takes over and forms everything. So our understanding through the Large Hadron Collider directly is related to what's going on and the first itsy bitsy fractions of the origin of the universe. So those are the questions that we are trying to answer. If you put Big Bang Theory on the internet, I don't know what to say, folks. It is so sad. This is what is going to come up, okay? So make sure and tune in. Definitely worth a watch if you like physics. But this is the real deal, okay? The real deal, and as many titles go, which is what I said, that the God particle is going to stay with us, and it probably has done a lot of service to science popularization. So too was the term Big Bang Theory, right? Everybody knows that term. And it was actually said in extreme sarcasm by an opponent, opposing scientist of the Big Bang Theory. He was doing a radio interview, and he was asked about it. He goes, "Oh, that Big Bang Theory," sarcastically, and it stuck. Okay, so to this day we talk about the Big Bang Theory. Big Bang Theory is one of our best models for how the universe arose. And it does describe, literally, not exactly, because you'll get into technicalities, but the idea that the universe arose from the tiniest, smallest, we call singularity, infinite point, and then started expanding. And when it did that, it started to cool off. So pretty much expansion, cooling off, very, very basic physics to explain everything. But everything of the universe's 13.7 billion years of life was decided in the first 3 minutes. Everything that had to happen happened in the first 3 minutes. And you think, if you don't put value to a second in your life, the entire future history or whatever of the universe depended on fractions of seconds in the early universe, okay? So look at that's what I said. We can't tell you what happened at t is equal to 0. But we could say with reasonable confidence what happened at t is to minus 43 seconds. Of course, as people, to me, that sounds like 0. But as a physicist, it's not 0. And that makes all the difference. Okay? So all the forces, the ultimate dream of the physicist is to combine gravity, weak nuclear, electromagnetic, and strong nuclear forces. So in the start, when the universe was born, everything was united. As it cooled off, insanely hot temperatures, 10 to the 32 kelvins. As it cools off, different forces began to separate out. Of course, the first force to separate out was gravity. Then you had the others bit by bit separating out. So today, these forces are separate. The aim of physics is to try and understand how they operate when they are united. And all that goes back to the beginning of the universe, to eventually give us 13.7 billion years later, 4th of August, us sitting in this room trying to figure out what really happened. So the question is, and that's what people are wondering, so there's this Higgs boson, which, because matter did not always exist, was hypothesized that for mass to exist, there must be a field, and that's the Higgs field. And that's what is actually the precursor to the Higgs boson. And if that field is disturbed, it could create the Higgs boson. All right, so you excite the field, and you can get that byproduct. So will it affect your life? Absolutely does. You are sitting here. You are not in the malls. You are not watching not Superman, what's wrong with me? Spider-Man or something in the theaters. You are here, right? So there's that aspect of it. Does it affect your life? Yes, it does. Does it have any practical applications? Not right now, okay? Because what the Higgs boson has been about is to test the standard model of the universe. All right, and it's funny, I had all these fantastic tidbits of conversation with a few of you before, and someone mentioned Carl Sagan, and how he's totally right. If you wish to make an apple pie from scratch, you must first invent the universe. So does the Higgs boson affect your life? Absolutely does. Because if we don't understand how it forms, how mass is obtained by particles, then we can't even, well, we shouldn't say apple pie for us, right? What we like, right? Anything, no favorite pie? Doubles, thank you, right? Yeah, now you're making me feel for one, right? So anything, to create anything, we need to have understood how all of this has really occurred. So has it solved all the questions that physicists and scientists have? No. At the end of the day, what it has done is that it has shown us that we are on the right track. And that's huge, right? $10 billion was spent to show that the theories of the physicists are on the right track. But it does affect your life, because every time you use a cell phone, every time you switch on a light or you use a digital camera, you owe it. These technology were developed by understanding how matter behaves on the smallest scales. If we didn't get that right, we couldn't control and manipulate it. All right, so that's where it is. But it doesn't answer a lot of other questions. It doesn't explain how gravity works, okay? It doesn't tell us how the different forces actually relate to each other. And there are all these things that we could talk for hours on: dark matter, dark energy. Doesn't shed light on any of these things, right? Dark, light. And it doesn't tell us why certain constants and electrical charges are what they are, all right? And it doesn't tell us why you exist made up of matter and not of antimatter, all right? Just a little quick aside rule to always keep in mind: if you ever go traveling in space, I inform my students, be very careful, do not shake hands with these other space travelers. They may look like you, they may behave like you, but it's possible they're made of antimatter. If they are made of antimatter, you are made of matter, and you shake hand, bye folks, okay? You will go off in a poof of explosion. All right, matter, antimatter does that. So that's an unanswered question. Why is there more matter than antimatter? How do we answer all these questions? Well, everything in life comes down to that last line, doesn't it, right? Well, not everything. Thought, the power of thought is absolutely a precursor to that. So the big deal with this boson is that it has proved the existence of the Higgs field. Okay, that's what I'm telling you. The prediction by the scientists was that there must be a Higgs field which, if particles pass through it, they endow them with the property of mass. All right, nobody had known if the Higgs field exists or not. The physics and the mathematics showed that it did. So that's really big. That's really big. If the things did not have mass, and that is your photon, that is your particle of light, everything would just be zipping around the universe and nothing would ever form into galaxies and planets and stars. So the biggest deal of them all is that it was the only prediction of the standard model in the general predictions that had not been verified. All right, so scientists were itchy about it. They wanted all the dollars. They built the biggest things and risked everything to see. And now that it has come out, it tells us, folks, we are on the right track. Do you see how huge that is? Okay? It's the story of 13.7 billion years. It's your story. It's a thought that began 3,000 years ago in India and in Greece. And in your time, in our lifetime, we are able to fit the pieces of the puzzles. All right? So the big Higgs boson, right, is easily the biggest advance in knowledge about the cosmos over the last 3 decades. That's why it's so much in the news, okay? Because of the missing piece that has been put together. And I close off now by saying, well, Albert Einstein is one of my favorites. I sometimes call him Uncle Albert. The most beautiful thing we can experience is the mysterious. It's the source of all true art and all science. And at the highest realm, I promise you that art and science coalesce and leads to, I will say, spirituality almost. With that, I'd like to end.
Well, I sense that there is a great feeling of satisfaction. But I was particularly pleased with the last comment of Dr. Haque when she said, religion is based on faith. Science is based on proof. Politics is based on neither faith nor proof. What I learned from the discourse, apart from being educated on this potential of this new discovery, which I will never learn in one lecture, but I get a glimpse of the concept of discovery. For each discovery, there are many more discoveries. And that has come out very much so in this particular lecture. And it is in that context, when we were walking on the hills, we were really trying to look at the discovery in politics. And we ended up that what we thought we had discovered, we had not in fact discovered. There are many more discoveries that have to be made in the field of politics. And it is in that context, I believe, that we have had a wonderful exposition on a very complex issue. Another lesson I picked up was that everything has structures, and that the universe has a structure. And the discovery of, quote unquote, the God's particle is getting at the very heart of the structure of the universe. And therefore the laws of physics is likely to be adjusted now to incorporate this new discovery in the way in which they have explained the structures of the universe. And it hit me immediately that in the world of politics, where I have spent most, in fact, all my adult life, that the issue of structures in politics is also relevant, and that perhaps we may need some physicists to come into politics to show us how to believe and understand structures in the world of politics. And that is why I end these brief comments by saying that I began to talk recently to myself firstly, and secondly with my pen, on what I call the logic of politics. After today's lecture, I have to question whether there is in fact a logic to politics if I don't understand the structure of that politics. And this therefore is an eye-opener for all of us. I want to thank Dr. Haque so much, not only for being here, but for so willingly agreeing to be here, and obviously for taking the time and trouble to prepare what clearly is an excellent lecture. And as a member of Parliament for Tunapuna, I say that we feel very privileged that you have joined us in this new program that we have started. Last week, or 2 weeks ago, we spoke about the making of a constitution. Today we talk about the structure of the universe. And I was told by my colleagues who helped organize this that the next session will be on the world information space, the controversy with that technology. So we are trying in this series to try and create an opportunity for the ordinary people who are not inside the university. Although I see many university people have followed you here, and that is to your credit. But we are trying to create an opportunity for the ordinary society, people in the society to come and have an interaction on these events. So I thank you once again, Dr. Haque, and I thank the staff in the department here for making this a possibility.